All right, I want to do one more example from section 3, and this one pertains directly to drift velocity. All right, so what is the drift speed of the conduction electrons in a copper wire that has a radius of 900 micrometers when it has a uniform current of 17 milliamps? Now assume that each copper atom contributes one conduction electron to the current, and that the current density is going to be uniform across the entire wire. All right, so for each atom, you're going to have one conduction electron. So first we need to start with using our value little n, which is, again, the atoms per unit volume, or the amount of molecules, amount of atoms, whatever it happens to be, in some unit volume. And to find that out, we can relate that to a couple of different things. First, we go from atoms per mole, which is just going to be Avogadro's number. Then you have moles per unit mass, which is the inverse of molar mass. So this is 1 over big M for molar mass. And this is going to be of copper, right? Because that's what the conductor is. And then we have mass per unit volume, which we know is the density. Right? And when you look at the units here, moles cancel with moles, mass cancels with mass, so you end up with atoms per unit volume. All right, so just to reiterate, again, we start with Avogadro's number. Moles per unit mass is going to be the inverse of our inverse of mass per mole, which is the molar mass, capital M. And the mass per unit volume is the density, or the density of the mass density of copper. So putting this into an equation, you have N is equal to Avogadro's number times the inverse of the molar mass times our density of copper. Right? Simplifying this is just Avogadro's number times our density divided by molar mass. Oops. All right. Now, taking that copper's molar mass, big M, and the density of copper, and this can be found in the appendix, making sure we have the correct units, right? We need kilograms, meters, etc. Right? So this is going to be N is equal to 6.02 times 10 to the 23rd moles to the -1, which is Avogadro's number, multiplied by our density of copper, which is 8.96 times 10 to the 3rd. Oops. And that's going to be kilograms per meter cubed. Divide this by 63.54 times 10 to the -3 kilograms per mole. Right? And this just ends up being 8.49 times 10 to the 28 per, so there's 1 over meters cubed. So what this says is there's 8.49 times 10 to the 28 atoms in every cubic meter of copper, right, which is a lot. And we can also say that's the amount of conduction electrons too, because we said that there's per atom you have one conduction electron. Okay, so let's go back to what we're trying to find here. We're looking for the drift speed, ideally. So we can start by looking at, start with our current density equation, right, which, as a reminder, is, capital J is equal to I over A. And we can sort of plug in some things that we've seen before. So we said that our current density is also equal to, so J is also equal to NE times our drift velocity, and we're trying to find our drift velocity, so we want to start with that. All right, and I'm just going to plug this into the equation. So when we combine this all together, you get N, which we just found, times the charge of an electron, or a proton, times the drift velocity, is equal to our current divided by A, right? And this A is going to be just the cross-sectional area of a cylindrical wire, so that's pi r squared. and putting in the radius they gave us, which was 900 micrometers, you have 2.54 times 10 to the negative 6 meters squared. All right, so now I'm just going to take this equation and rearrange it and solve for our drift velocity. So that's going to be I divided by A and E. Plug everything in, so we have 17 times 10 to the negative 3 amps divided by 8.49 times 10 to the 28, 1 over meter cubed, times 1.6 times 10 to the negative 19 coulombs, which is, again, the charge of an electron or a proton, and 2.54 times 10 to the negative 6 meters cubed. All right, solving this out, we find that our drift velocity is 4.9 times 10 to the negative 7 meters a second. And just to relate this to something that we might be able to reference, it's about 1.8 millimeters per hour, right? So that's very slow. So we think of electricity, as going very quickly through wires, but in reality, the net movement of electrons is actually very slow. All right, that's it for this video. Next time we're going to be looking at resistance and resistivity.